Hey everyone, in this video I'll be going through the questions that I set at the end of the first lecture on S-block elements, lecture 4, and working through the answers with you. Question 2 is asking about the reactions of a couple of group 1 metals, and it wants us to predict the products and write balanced equations for the reactions. Now I mentioned in the discussion session, but not in the recorded video, to avoid doing question 2c, and this is because it talks about nitrates decomposing. So we're going to be looking at that in the next lecture, lecture 5, and that question will be at the end of the next lecture. So the first one is adding cesium to water. So you'll remember that when all of the group 1 metals are very reactive with water, they've got to be stored under oil for this reason. So it happens quite violently. Also, the reaction gets more violent as we go down the group. So where we're looking at cesium, it's the most explosive of them. But how reactive it is doesn't make a difference to the reaction equation or the products. So we're taking cesium and adding water. And the product of this is cesium hydroxide, but also hydrogen gas. Now, usually, especially when we're down the bottom of the group like cesium, the reaction is so exothermic that this hydrogen will actually explode. And as we need to balance this first, actually, because you can see it's not balanced. So it's 2 equivalents of cesium and 2 equivalents of water make 2 equivalents of cesium hydroxide and 1 of hydrogen gas. Now, as I was saying, how far up or down the group it is, how violent the reaction is, doesn't change the stoichiometry or anything. So for all the group 1 metals, the general equation is the same of 2M, if M is a metal, plus 2 H2Os makes 2 equivalents of group 1 metal hydroxide and hydrogen. Part B of it was looking at burning rubidium in an excess of air. So let's write that one first. So it's really the rubidium reacting with the O2 in the air. Now this one does change as we go down the group. So you remember that larger cations are stabilized by larger anions, and this is evident throughout the group 1 metals reacting with oxygen. So at the top we've got lithium, which is very small. If that was reacting in air, it makes lithium oxide with the O2 minus anion. Sodium, we get sodium peroxide with the O2 2 minus, and then from potassium down, so rubidium as well, because that's below potassium, we get the superoxide, which is RbO2. An anion here then is the superoxide anion O2 minus. So question 3 is asking us to use a Born-Haber cycle to explain why sodium chloride, as in NaCl2, dichloride should I say, doesn't exist. So this will be the longest question because it's got quite a few steps to do what seems like a simple question. So I've got all the information from the book at the top here. I've written ionic radii Mg2+ and sodium 2+ as 72. This is just because the book doesn't give you the value of sodium and tells you to take the value of magnesium. So we're not doing anything with magnesium, but just to make clear that sodium 2+ radius isn't really 72. So first off, we should start by writing the equation of what we want to find out. So we're looking at whether we can take sodium, we'll start in its solid phase, and chlorine at Cl2 as a gas, and mash them together to make NaCl2. And the data that we'd get for this is the enthalpy of formation. So that's the really important thing. We need to know that enthalpy of formation. Is it endothermic? Is it exothermic? Is it a very large value of either of these? And that will give us an indication of whether it's likely or whether it's stable with respect to its elements. So then for Hess's law, we can go through step by step, add up all of the enthalpies for all the individual steps, and they'll equal the enthalpy of formation. So let's draw the rest of the steps for this Born-Haber cycle. So the first one is making the sodium gas phase, and that is by atomizing it. So we've got the enthalpy of atomization there. We then need to turn it into Na2+, because it's going to be in an ionic structure with 2 negative charges to cancel out. So first goes to Na plus with the first ionization enthalpy, number 1, and then we add the second ionization enthalpy, number 2, to make it Na2 plus. Now this is going to react with Cl minus, so there's one less step for this one. So we take the Cl and we atomize it again to get 2 chlorine molecules, atoms, should I say, very clear, atoms in the gas phase, and that is with the atomization enthalpy. And then we turn them into 2 Cl minus anions by using the electron gain enthalpy of chlorine. And then we add together Na and Cl gas phase ions to make sodium chloride. And this is with the lattice enthalpy. Although, importantly, if you remember the definition from the second lecture of a lattice enthalpy, it was the energy given out when we take a mole of a solid and break it up into gaseous atoms. Now we're doing the opposite. We're taking the gaseous atoms and putting them together in the solid. So this is a negative value because it's the opposite of the lattice enthalpy. We're actually going to go one step further. We don't have the lattice enthalpy, so we need to calculate it using the Kapuscinski equation, and that actually gives us the lattice energy, which is delta lat U. But this is close enough to the enthalpy that it'll suffice for our purposes. So as I was saying, to get this lattice energy, which is our first step, we need to use the Kapuscinski equation from the second lecture. And if you remember, that was K, which was a constant, adding up all like the Madelung constant and the Born exponent and the Avogadro's number, cancelling all of that into one nice value with non-standard units so that we can use a picometer radii, for example, and getting our a molar value at the end. So that was really neat. So the constant K, nu, which is, that's my really bad nu, it looks more like a V in reality, which is the number of ions in the structure. Z plus, which was the charge on the cation, Z minus, which is the charge of the anion, and this is all over the radius of the cation plus the radius of the anion. So if we plug the numbers in, the constant is 107,900. Nu is 3 because we've got sodium and 2 chlorines. The charge on the cation is 2 because it's Na2 plus, and the charge on the anion is 1 because it's chlorine 1 minus. And then this is all over the radii added up there at the top, so 72 plus 181. And if we do this sum, it gives us a lattice energy of 2,500. It actually gives you 2,558 point something. We're going to round it up to 2,559. The book goes one step further and rounds it all the way up to 2,560. So our value will be 1 off what the answer that the book gives, but we are 1 kilojoule per mole more accurate than the book. So take pride in that. So we've got the value of this now. All we need to do is work out the formation enthalpy. And as I was saying, from Hess's law, all the steps of the cycle added up will get us the delta F enthalpy. So we'll do step by step. This equals the enthalpy of atomization of sodium, so 108, plus the first ionization enthalpy of sodium, which is 496. The second ionization enthalpy, which is much larger, that's 4,562. And now we have to start thinking about stoichiometry as well when we get to chlorine. So first off, we need the atomization of chlorine, but we need 2 times that. Because if you look at the data up here, this is the atomization enthalpy to produce 1 chlorine atom. We're producing 2 of them, so we need to add in 2 times the atomization enthalpy. And for exactly the same reason, we're then going to add 2 times the electron gain, because again, it's an electron gain for 1 chlorine atom. We need to do this for 2 chlorine atoms. So 2 times minus 349, and then minus, because you remember the lattice energy was negative, 2559. If I open up the calculator on my phone, this gives us a value of 2151 kilojoules per mole. Now this is a super endothermic reaction then, really high energy, and this shows that it's not stable with respect to the elements. So then, yeah, this is why NaCl2 doesn't exist. We can delve a bit deeper and see, yeah, specifically what part of this makes it not exist. And I'll highlight it in green. It's really this step. So the second ionization of Na plus to Na2+, this takes loads of energy. And yeah, that's why it's just not possible. It just isn't stable. And I guess we can go one step further with the reasoning. Why is this second ionization enthalpy so high? And if you think back to the first video, this was because we said that if you're trying to remove an electron from a core shell, that takes a lot of energy. And yeah, since sodium is an S1, is group 1 metal, we do the first ionization and it takes that S1 electron. Then we go into an inner shell, which takes a lot more energy because it's much closer to the nucleus. So that's why the NaCl2 won't exist, and it is in the form NaCl. So again, a deviation from what I said in the lecture video about which questions. In the discussion session, I said to skip question 4. This is again because it deals with nitrates and carbonates, which we'll be talking about in the next lecture. So we'll do question 4 next time. Question 5 is giving us a series of reactions and products of a group 1 metal and asking us to identify what these various metals and products are. So to summarize it, the group 1 metal, which is M, burns in air to produce X. This then reacts with water to form Y. The metal itself, M, also reacts with water to form Y and gives off combustible gas Z. And upon heating, Y, this gives off steam and forms X. So we've got 4 things we need to find out: M, X, Y, and Z. And I'll take you through each reaction in turn and how we can work out which is which. So M burns in air to produce X. Since it's a group 1 metal burning in air, we know X is going to be an oxide. Obviously, which oxide depends on what M is. The oxide reacts with water to form Y. Now group 1 oxides reacting with water to form Y always form a hydroxide. So we know that Y is going to be some sort of hydroxide. Again, depends which metal it is. The metal itself also reacts with water to form Y, the hydroxide, giving off combustible gas Z. Now this we looked at in the last slide actually, question 2b, when it was asking about rubidium reacting with, cesium reacting with water. We said about the combustible gas Z and how the reactions of metal with water are always of the same equation, and the combustible gas Z was hydrogen. Finally, upon heating the hydroxide, this gives off steam and forms X. Now this is really the key to solving the whole question, because if you remember back to group 1 hydroxides, the only group 1 hydroxide that will decompose upon heating is lithium. So we then know the metal M is lithium, therefore the oxide X is lithium oxide. Now going back to what I said on the last page as well, the oxide depends on whether it's a small or large. Lithium's at the top of the group, so it forms Li2O as its oxide. And then Y we already said was a hydroxide, so we know now that's going to be lithium hydroxide, LiOH. So question 9 is dealing with the preparation of magnesium chloride from seawater and asking us to work out the equations of the whole process and then also looking at the waters of crystallization. And this one is actually marked as one of the harder questions in the book with the asterisk. So we'll go through the question, and then there's a couple of equations. So magnesium chloride is prepared by reacting seawater with calcium hydroxide, and this precipitates magnesium hydroxide. Then subsequent reaction of magnesium hydroxide with hydrochloric acid, and then slow evaporation gives crystals of magnesium chloride. So there's actually 3 equations that we need to get, which I'll try and fit in here, because we need even more room underneath for the next one. And we'll take it step by step. So the first one is it's reacting seawater with calcium hydroxide to precipitate magnesium hydroxide. So in the videos I was mentioning how magnesium is actually one of the most abundant ions in the sea. It's the second most abundant cation in seawater. So we're actually looking at it as Mg2+ from the seawater, and then reacting this with calcium hydroxide, and that will give us the magnesium hydroxide, like the questions told us, and calcium 2+ cations. And that seems balanced as it is. The second 2 steps are a bit trickier, because you almost expect this just to be one equation, the reaction of magnesium hydroxide with hydrochloric acid. But it's not. The reaction with hydrochloric acid and the evaporation to give crystals of MgCl2 are 2 separate processes. So the first one is the magnesium hydroxide, which, since it's a precipitate, remember, is solid, and reacting that with the acid. So we're looking at magnesium hydroxide, MgOH2, reacting with H3O+. So these are protonated waters from the fact that it's in an aqueous acidic solution. And what this does is form magnesium 2+ ions, again, and more water. So this is a way of getting everything in solution. And this one isn't balanced. You can see already the charges balanced, unbalanced, and that's the one. So we're going to need 2 H3Os to balance the charges, and then we end up with 4 waters at the end of it. So finally then, we've got all our ions in solution. We've got the Mg2+, and we've also got Cl- in solution from the HCl, the other part of the acid. And then these react together under evaporation to form the solid structure MgCl2. And then obviously we've got more chlorines on this side, so we need to give 2 Cl- there. And this is because this magnesium chloride is soluble, so in solution we just have these 2 ions as we've drawn it on the left hand side here, magnesium 2+ and Cl-, and then it's upon evaporation of water that these guys get together and form the MgCl2. Now the second part of the question is a bit longer, and it's not really something we went through in the lecture, the waters of crystallization, but it's good to know how to calculate them. It's something you may have done introduction to chemistry or high school, I'm not sure. There's also a nice link down here in the bottom left, I'll put it in the description of the YouTube video, to a BBC revision guide on calculating water of crystallization, but I'll go through it now as well, using the same way they do in the bite-sized guide, so you can read it with from 2 different perspectives. So it says a sample of magnesium chloride obtained this way contains 18.5 weight% of magnesium. It's written slightly different in the book, they say percent by mass, but it's the same. Assuming that there are no impurities, how many molecules of water does magnesium chloride crystallize with? Now, it's a bit tricky, but there's some quite easy steps we can follow to do this, and this is the same as working out the empirical formula, which is something you probably did quite a few years ago, with a couple of steps. So we need 2 columns, one for the thing we care about, for magnesium chloride, and one for the water. And then we're going to work down in rows. So at first we're going to put the mass of each one in. So the way I've calculated the mass is it gives us a weight percentage of magnesium. So we'll just pretend there are 100 grams of product obtained this way. That makes everything much easier, because then it means there's 18.5 grams of magnesium. And then by using the molecular mass of, or the atomic mass of magnesium and the molecular mass of magnesium chloride, these are 24.305 for magnesium, and then 95.211 is the molecular mass for MgCl2. I won't go through this equation, but I've done it beforehand and written it down. We get to a mass of 72.47 grams of magnesium chloride. So basically we know there's 18.5 grams of magnesium in 100 grams. Divide that by the atomic mass of magnesium to get the moles of magnesium, and times it by the molecular mass of magnesium chloride to get the mass of magnesium chloride. Then the mass of water just makes up the difference. So we've got 72.47 grams of magnesium chloride, the other 27.53 grams to make it up to 100 gram total is water. So then again, we need the molecular masses. So that is 95, as we said before, 95.211 for magnesium chloride, and let's just say 18 for water. And then we divide the first row by the second to work out how many moles we've got of each. So 72 divided by 95 is 0.76. And water, we end up with 1.53. Sorry for my jumping between a decimal point and a decimal comma. That's what happens when you go from Britain to the Netherlands too often. And then, much like we did with the empirical formula calculations, or you would have done high school or whatever, you divide them both by the smallest. So let's just write divide here. And then we end up 0.76 divided by 0.76 is obviously 1. And then 1.53 divided by 0.76 is 2. So then we know that the formula is MgCl2 dot 2 H2Os. So yeah, it crystallizes with 2 molecules of water for every molecule of magnesium chloride. The final question is about the structure of beryllium chloride, and actually relates a lot to lecture 1 with VSEPR and valence bond theory. I'll go through in the worked questions for the first lecture. There'll be a more detailed explanation of how to use VSEPR, but yeah, we'll have a brief one here. So just to refresh, we've got the beryllium centers, which are these light green ones, with bridging chlorine atoms in between them here. Now, the one feature when we were talking about the bonding in beryllium chloride is that for each one, 3 of the chlorines are covalently bonded to a beryllium center, and then another one is a lone pair from a chlorine forming a dative bond to a beryllium center. But it's important to know that even though this is a dative bond, it is still a covalent bond. It's just both of them come from one atom rather than one from each atom. So everything about VSEPR and the bond angles, they're not changed at all because it's a dative bond, which is nice. So to work out the geometry, we just do it how we did with all the VSEPR. So we look at how many electron pairs, so bonding pairs and lone pairs, are around the central atom. So if we take the beryllium center here, it's got 4 bonding pairs around it, here, 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 and no lone pairs. So it's got four electron pairs, and that means it's got a tetrahedral geometry. A value for the CL-BeCl bond angle. So this is directly related to the geometry. We know that if there are no lone pairs and all of the electron pairs in a tetrahedral geometry are bonding, that means there's a bond angle of 109.5 degrees. And finally, what's the most likely hybridization of the beryllium atom? Now this is going back to the valence bond theory we talked about and the hybridization of s and p orbitals. So in this case, to make a tetrahedral geometry, we have to have the hybridization of one s orbital and all three p orbitals. So the px, I think this one's pz actually, and in and out of the board by, and they form the sp3 hybridized orbitals that look something like that in all of the directions of the tetrahedron. So that's it. The hybridization of the beryllium atom is sp3.